Okay, good afternoon. So far we have 4 people signed up here. I get a little display that shows how many are, who's on. And up to about 6 I can see who's here, but beyond that your name goes off the bottom. It only displays the top 6. So anyway, that's okay. As long as you guys are watching the lectures. We have 4 more classes. We have 4 more classes. So we have let me problem sessions. Problem sessions. April 25th, 27th, and May 2nd and 4th. Then that's it. And then we have our final exam, which I will make sure that you all have the information as to where it is. It'll be in Keller, Hall 125, just like our other meetings of the class. But I want to talk about the homework. The next homework will be homework 9, and that will be the last assignment. I can't very well give you a homework problem on the last day of class and then tell you the exam is next week. Well, I could, but Anyway, that'll be the last assignment, and it will be posted in our Google Drive, posted tomorrow. So that'll be April 21st, Friday, and due May 5th, which is also a Friday, and that happens to be the last day of class on the university, on the campus. That's the last day of class. Because the University of Minnesota starts the spring semester the day after. No, I'm sorry. It doesn't. It starts it in about the 18th of January. Anyway, this is our end date because we're on a quarter system. This is really called the spring quarter. It's called a quarter system, but there are not 4 quarters. There is a summer session that's chopped up and taught very differently if you've ever been here for a summer course. But the classical classes in the United States and the classes at Rensselaer when I was an undergrad went into June. June was the month when you graduated. June was the month for final exams and final grades. But here we moved it back. Not by choice of the university. Interestingly, this was dictated to us by the state of Minnesota legislature. They wanted us to be synchronized with all the other schools in the state for various reasons that I know. Anyway, we used to have semester systems that were 2 16-week semesters as opposed to the 10-week quarters that we have now. Anyway, I'm sorry, I'm backing off on this. We used to have quarters. We now have semesters that are 16 weeks. we used to have quarters, and the students loved the quarter system. They loved the quarter system. We had a fall quarter, and we got off in December. And then the winter quarter started the day after New Year's, and we had a winter quarter and then a break in March, and then a spring quarter that ended in June. That's the old schedule. And the students liked it, the professors liked it, because they were shorter. As one student said, if you got a lousy professor, you were only stuck with them for 10 weeks instead of 16 like we are now. The legislature came along and said, you will switch to a semester system. I'm mixing here. So we're on a semester system. We start the 18th of January, and we go till May 5th, which is unusual that classes end in May, as do a lot of the graduation ceremonies. Anyway, be that as it may, here we go. What I want to so I want this assignment is going to be you're going to have 2 weeks to do it. It's got a lot of work. I'm going to work you hard to the end here, and that will be the end of the course. So we'll start back. Now, what I want to talk about today again is this business of deregulating the power system. Remember, we said so. Let's see, deregulate. An alternative word is to privatize. I'm going to put an extra vowel in there. Privatize. In some countries, like Norway, for example, everything was government run, and they then privatized them. I don't know how they decided that, but the generating companies, which in Norway are groups of hydroelectric dams, became private companies that were going to compete. And the network itself is the government, is still run by the government. In the United States, we didn't have to privatize because the companies were privatized. But what we asked them to do is to separate out their generation business from the transmission business. The thinking being that if a competing generating company was going to use my transmission system and compete against my generators, maybe I would say, oh, sorry, but the transmission system isn't working today. And so there was this issue. They used to argue that if you had a control center that was at one time controlling transmission and this generation, that you had to have all kinds of restrictions and so forth. You had to. People couldn't talk to each other. They were often placed on different floors of the building. And in California, the first California ISO system, I'm chuckling because it didn't really work any better. They put the transmission control systems in Folsom, California, and they put the generation control systems down near Los Angeles. They figured that way, it would be harder for people. Of course, we have telephones and the internet; they could talk if they wanted to. And so eventually they dropped that, and everything's done in Folsom, California. I also used to find that interesting that they built the California ISO in the same city in California as their largest prison, or one of their large prisons, Folsom Prison. I used to joke and say that's because they were hiring the prisoners as programmers. All right, so much for the humor for today. But privatize. And the idea being that private GenCos, okay, remember that? Private GenCos would compete. They would compete. Now, part of what part of the drive towards deregulating like this was that if they were going to compete, then the generator owners, private companies, had a very big incentive to operate their plants as efficiently as possible, and to modernize. And if they had really old equipment, they probably couldn't compete. So if they ended up buying an old plant, they would have to upgrade it and so forth, or replace it. But that's part of the idea of privatizing. Whereas under the old system, the vertically integrated company would build a generating plant and just operate it, and the Public Utility Commission would guarantee that they'd get a certain rate of return. There was no incentive to upgrade the plants early. They would run the plants out for a very long time. Now, the PUC, under the old system, would also not want them to be replacing plants too soon, nor to try to run them for too long. It's not like the efficiency was that much different, but under the competing system, they had a big reason to keep their generators competitive. Transmission systems were also privatized. We talked about that, and they don't compete, but they do operate as independent companies and charge for the use of their service. So it's a different model than competing with somebody. Now you could say, well, they compete with other transmission companies. Yes, but that's the fact is there might be competition if one company ran a really good transmission system and a neighboring one had one that was breaking down all the time. And if I was going to build a new generating facility, I might try to put it in the so that I could attach to the really reliable system. That's one of the possibilities. Distribution companies, you already have that kind of thing with municipal utilities. Small towns, many of the small towns and regions in the United States, in the farming regions where we live here in the Midwest, already did that. You had a municipal utility that had a high voltage substation. They buy power, drop it down to some distribution voltage or maybe some sub-transmission, and then but they ran a distribution system for the town. They didn't operate generators, and they could buy power wholesale. They could buy it now. That meant they could buy it from any generator if they wanted to. Okay, but we talked about the fact that one of the things that started driving this was this term open access. And open access came along. It's interesting to me how it came along. One of the things that happen is that you might have a thing like an oil refinery. And the oil refinery has huge boilers to produce steam. And the steam is used in their processes, their chemical processes to refine oil. Now, the people, I am having difficulty here. Well, I'm going to keep going. Having difficulty with my computer. My monitor keeps flicking off. I thought I had it set so that, you know, don't shut down. Once I turn you on, stay on forever so that it doesn't shut down in the middle of the meeting. Well, it keeps shutting down, and I keep moving the mouse. Anyway, the oil refinery produces steam. Well, they don't use the steam all the time, so what they'd like to do is they'd like to take the steam during certain hours of the day and run it through a turbine, and that's connected to a generator, and then they would sell power. This went by the name that's a C, cogen plant. Cogen plant. Houston, Texas, obviously big on oil, huge center for a lot of oil companies, and they have not just oil companies, but companies like Dow Chemical and others. And Houston, Texas has a lot of this kind of cogen available. Well, they came back to the government and they said, we have these boilers that produce steam, and in fact we can produce our own electricity, but we have more steam and more capacity in these generators than we need much of the time for electrical needs of our plant, and we'd like to sell the excess. But the power companies won't let us hook up. You know, there's this kind of thing. And the power companies maybe hooked it up and said, okay, we'll give you a contract. And the oil refinery said, we want to basically compete. So this is the start of an independent generator, which is competing to sell. Okay? Competing to sell in the marketplace. I am trying to think of another thing where people buy things, and some of the manufacturers, it's just a spin-off of part of the rest of their business. But be that as it may, here we've got this oil refinery, or we have a Dow Chemical or something like that, and they've got huge amounts of capacity boilers, and so they have their own generator, but they'd like to be able to get out there and compete and sell. And so you had this whole idea of open access, and the rules said, okay, you know, they used to say something to the effect that you paid them at the highest incremental or marginal cost of the generators on the system, and it meant it really wasn't fair, because they got it gave them an advantage, and that system was in existence for a while. But now they can be an independent generator. There's rules. The government said, okay, you can set up standards and rules as to how people get on this. But you know, we showed this the other day, that here's our power company, and let's say he has generator and load, and then over here comes the green power company, and so it's in green, and the green power company builds a short transmission line and connects. And the electric utility over here had to allow this, and had to basically help them and you know, set things up. Maybe they had to put up some equipment in their substation, and so on and so on. I don't know. There's probably cost sharing and things once in a while, or maybe they built this line over. In any event, this guy can now compete with the utility's own generators, and can sell into the system. So that was the idea of open access. Well, the whole idea eventually came down to, well, we're going to do this for all the generators. Then we're going to do it, and we're going to have a market. Now, we talked about the market last time. And we said the market is going to use an auction. Uses an auction. The auction is a mechanism to sell things when you can't look up a price for it. One of the auctions that I watch quite a bit, there's a program on the cable channel called Chasing Classic Cars. And it's about a guy in Connecticut that owns a shop. But his specialty is to buy cars, fix them up often, and then he goes to these auctions and sells the cars. And the reason he goes to an auction is that there might be, somebody publishes a book and says that a certain car that was, let's say, built in 1949 Ferrari, okay, and how much is it worth? Well, what they'll do is they'll publish and they'll say, well, this is what these cars have been selling for. But that doesn't mean that the market won't pay more or maybe less. And so you go to you go to the auction, and the auction has people sitting around who have lots of money in their banks because some of these cars that get auctioned off can go up to $1 million each. Normally they're in the hundreds of thousands of dollars. These are exotic sports cars, and sometimes they're exotic antique cars. Stutz Bearcat. If you don't know what that is, look it up on Google. But there were a lot of cars built in the United States, which had a run of business that lasted 10 or 20 years, and then the company went out of business, as well as some of the original Ford, GM, Chrysler cars. And there's a market for those. There's a market for all of these different kind of cars. But what are people willing to pay? And you don't know until you go to the auction. And you put the car up, and some of them will put up with a price that says if it doesn't get to at least this much, that's it. So you can put item up for sale in the auction with it's just a breakpoint price, or I forget the name that they apply to it, with a price which must be met. So that's a minimum. And if a minimum price, and if the car doesn't get up to that minimum price, then forget it. The guy who brought it into the auction has to put it back on some truck and take it back. Other times they put into auction with no minimum, which makes it very interesting because the guy might be hoping to get $100,000, and the bidding goes no higher than, let's say, $65,000. Well, that's all he gets, and that's maybe he's remorseful that he brought it there, but that's it. And so an auction is a mechanism. Let me put this down. mechanism to sell when there is no known price. Okay, no known price, which means that some people might look at a car and say it's that thing is no great. They made a lot of those cars. There's a lot of them around, and so I wouldn't pay more than $20,000 for it. But some other guy just wants that car and keeps bidding until he or she outbids the rest, and so maybe it gets sold for $40,000. There's no catalog. Now later on, they may put in a journal or something. They may publish what the car was sold for, and that kind of says, well, that's what the market is paying these days. But it all depends, as this guy on that auction show for cars says, it all depends on who shows up. Well, it's the same thing with in the case of an electric power auction. No set prices. Now, one would assume that generators do not want to price their energy below their costs. However, it does actually happen. In the wee hours of the morning, well, let me back up here in a minute. We'll talk about how this auction thing works and how they actually administer. They don't sit there and say, okay, how much am I bid for this? How much am I bid for that? Because they have all these bids that come in, but there's no set prices, and so we use an auction. And by doing it with this clearing price, it helps to guarantee that there's no advantage to underprice, meaning below actual cost, and there's no advantage really to overprice, because you may not get selected. Your bid to power, if you say I'm just gonna put in a bid that's twice my actual cost, and I'll make a lot of money, and other people will sell what will be below you in price. So if you overprice, you may not, we'll put it this way, get in. In other words, you may not get selected. All right, so that's why they use this kind of thing. The auctions run in the following manner. Well, before I go into that, what I want to talk about is the mechanism of actually doing this. We allow generators to bid, and we do this right now. I'm just going to say the auction runs for 1 hour, and so you're bidding to supply power for a certain hour of the day. that's very important, because if you're bidding to supply power at 2 p.m. in the afternoon when the load is very, very high, that means a certain strategy. If you're offering to bid at 1 a.m. in the morning when there's almost no, well, a low load, you bid in a different strategy. But you allow the generation to bid into the auction. Now, we showed blocks. A certain in the block can go from 0 to, let's say, 100 megawatts at a certain price. Let's say $15 per megawatt hour. That means that you'll sell 5, 10, you'll sell all the way up to 100, and this is the price. Okay, that's the price for part or all of this, part or all of that block. Now, what that says is that it says, well, it looks, if you will, like a generator, and it has a max of 100 and a min of 0. Okay, and it goes like this. And the top here is $15 times 100, so this is 1,500. There's the total dollars per hour, but we're pricing it, and so the slope equals 15. Now, when they do this, they can put multiple blocks in, and so if a generator has a cost function that let's say starts and it actually goes up like this to some max, and we've been used to doing that. Well, we come along and you break it into, let's say, we'll do it real crude, three pieces, and we'll just make linear chunks out of them. And there's and I bid 3 different blocks. Now, be assured that the way this thing works is, if you bid a block down here, it's not going to tell you that it wants the upper a block here without first filling this entire lower block. Then it'll start buying of this block, and then it'll start buying here. So it'll always do the purchasing first from the lowest price, then from the next lowest, etc. So you by putting blocks in, we convert it. And we already talked about doing linear segmented functions. Well, that's what a block price is. So what we're working for now is the next step in this process. So the generators put in blocks, as many as they want. The generators can bid blocks, or they can bid a cost function. The generator can say to the market operator, here's a quadratic function that represents my costs. And so instead of putting blocks in, he gives them this function like this. And you think about it for a minute and you say, well, then how does that get into an auction? And that's where we're going here in a couple minutes. But what I want to continue with here is, you can bid a cost function, And part of the bid is the generator minimum, the generator max, the startup cost, minimum uptime, minimum downtime. This all begins to look like unit commitment, and that's what it is. So what we're going to do is we're going to see here that this process ends up working its way into a system that we already understand of unit commitment and optimal power flow. Well, getting ahead of myself. Oh dear, come on. I have to repair that with Scotch tape to get it to go through my scanner without balking there. Okay, so the other thing that we allow, loads, like a large factory, industrial center, municipal, utility, etc. Can go out and buy power, and the load. What is it? It can bid a block of load purchase. Let's put that word here. So it can say, okay, look, I'm willing to this is what I'm willing to pay, and here's let's say 50 megawatts, and here's a price of, let's say, $25 per megawatt hour. So I'm saying that I'm gonna bid 50 megawatts, and it's actually 0 to 50 at a price of $25 per megawatt hour. I'll buy load up to 50 megawatts at that price. And if you remember, this represents a bid into the auction. Well, we talked about this earlier, that economics says that we always want to maximize the benefit of the auction and of an economy, and we're going to maximize over all the loads some function Wj of Pj, and we're going to subtract from that our standard cost of generation. We're going to maximize this function. Presumably, and it would always have to be the case, the benefit to buying power is greater than the cost of buying it, or else they wouldn't buy it. They wouldn't buy it if the cost ultimately was more than the benefit. So that is, and that's this is the that says that an economy is runs best when we do this. Well, I mean, there's constraints and so on. We're gonna put them in a minute, but we usually minimize so that we can say this as a minimization of Ci of Pi minus Wj of Pj. So this is the generator cost, and this is the load benefit. And when the generators bid, bids reflect the cost. And similarly, when the loads bid, load benefit. Well, the benefits reflects their bids. So the load bids into the market and says this is what buying the power would be worth to me. They hope they can buy it much cheaper, but they said that's what it would be worth. And if you're going to try to price your generation above what it's worth to me, I'm buying zero. The whole process comes to a halt. So the generator bids its costs, the loads bid a benefit function, and inside we say, well, we're minimizing this. We're minimizing this function. And we'll see in a minute where I'm going here. Why don't I put the dramatic announcement here, and that is that the auction can be done using an optimal power flow. So this is the kind of function that we put into the optimal power flow, and what we do is we have functions here that look like this for a load, but we enter them as negatives. That's why I put a negative in here, and you'll see this in the homework and in the problem that I'm going to go over here in a little bit. So we can put generation and load like that, and then other than we said that there's mins and maxes on these. Now you can put them in as blocks. You can put you need to say that the sum of the PI generated must equal the sum of the PJ load that you end up putting in the market. So we have to have a balance. We have to have load, generation, balance. This OPF can be done with an AC OPF. Okay, wherein you'll get losses in there too. But let's just talk about it now for a DC or linear power flow. And so we end up with a constraint that says the sum of the PI over the generators minus the sum of the PJ over the loads equals 0. It doesn't dictate how much load is sold, but it does say however much load gets sold, that we have to, and if we have a lot more bids for load than generation available, well, some of it doesn't get satisfied. If on the other hand, so if there was a shortage of generation, well, these guys would all be at their max, and some of the load wouldn't be sold. If the generation has much more generation than load, and the prices are right, all the load will get sold, and then generation will go unsold, and that just takes care of it inside. So we can bid these things, and actually an OPF we can solve it with, if you're doing the bids, if the bids are simply linear segments like this. Here's a certain megawatts at a certain price. Let's say a price. A lot of times they like to use lowercase p. P sub I, megawatt is megawatt sub I. Then I can use linear programming. I can use linear programming. Now, what is even better? What is even better is that I can use the fact that I have minimize the sum of Ci of Pi minus the sum Wj of Pj, subject to the sum of Pi minus the sum of Pj equals 0. I can also have line flow constraints. I can have contingency constraints. So it doesn't matter. Sorry about that. I should be putting my demarcation line on here. Anyway, so I can have a complete optimal power flow where these are bids, and these are bids to buy, bids to sell. You can do when all you have is the top two constraints. It's relatively, you can do it on a spreadsheet or something. You order up the generator bids and the load bids, and you can work out where the clearing price is without any regard to network constraints. As soon as you put network constraints in there, you have to have an LP or a quadratic program. So if they were bids like this, now the bids could also be a quadratic function. So that's for the gen, and the load basically has a quadratic function, only we're going to negate it, right? We're putting a minus W here, so it gets negated. And so we don't need to do it in blocks, and we can use quadratic programming for this to get. And I'm gonna do an example now that we'll attach with the notes, and this is a problem that I gave students probably several years ago, maybe even almost 6 or 7 years ago. And I'm going to show you this here, and I'll mark it up a little bit. But so I said to start with, we're going to have our standard 6-bus system, and I have 2 generators on each bus and 2 loads on the load buses. And in this case, the generator buses don't have loads, and the vice versa for the load bus. So these have loads on them. Okay. And here's my bids. So these are the generator bids here. And the prices go from 50 up to 130. And these are single linear blocks, okay? They're single linear blocks. And here's the bus number. So that's bus 1, 2, and 3. So this is an auction, and bus 1 has got really cheap power. Maybe he's got hydro units. And then bus 2 is he's got 75 and he's got 120. And bus 3 has 100 and 130 power. So we can set this problem up, and we can solve it in a standard way. Remember, is you order the generator bids from lowest to highest, and you order the loads the opposite, from high to lowest. Well, the generator bids are gonna almost follow this table, but I'm going to list them here: 70, 75, 100, 120, 130. So, and you can look back at the first page there. It shows you the generator bids. And I got to put that, well, here they are here. And so this is the price, and the megawatts of the block are 200, 100, 200, 200, 180, 40. Okay. And one of the first, and so if I said I wanted a certain amount of power, then I could just say, okay, this one, until I get to an amount where if I buy the whole block, I'll have more than enough, so I buy part of the block, and I'm done, and the rest doesn't sell, and that's the clearing price. Now I'm going to do loads on the other hand, and the loads would start at, so here we went from lowest to highest, okay? Low to high. Here we're going to start out with the highest generator, which is 250, pardon me, 250. And then, let me write this, 250. And then it goes down to 200, and then it goes to 150, and then it goes to 130, 110, and then 90. And the megawatts that go with that is 200 with no, this is 100. 100, the 200, this is 200 here. The next one is 150, that goes to 150. Isn't that interesting? It just matched it. 130 has 200. 110 has 150, and 90 has 100. This has a total offered of 2, 3, 5, 7, 880, 920. This one has what? 1 and 2 is 3, 4, 50, 650, 750, 8, 900. Okay. So this is it's close. And what happens now is we just say, okay, you always match the lowest price generation to the highest price offer from the load. So we say, okay, this is 50, and this guy's willing to pay 250, so we buy that one and we sell that one. This one is 100, so we buy that from here. We still have 100 left, and so we now say, well, I still have 100 up here, and that's below the 250, and you come down the thing like this, okay? You come down, and it clears. I'm going to let you do that in your own time, but it clear at $110 per megawatt hour. Okay, it clears. And if we put this into a one of these drawings, remember, this is the supply function is here. This is the demand. And this micro print on here, this says loads bid to buy, generators bid to sell. Okay, supply, and that's the generators, and this is the demand, obviously, it's the load. And we start with the highest load, and so here's the load coming down like this. Now, in the LP, those get entered as negative numbers. We've talked about that. these get entered as positive numbers. But this is really the prices. And so you've got this supply curve coming down here. And it says if the generation only costs 50, we'll sell the whole thing to this 250, and we'll sell it to the $200 one, and we'll sell it. So these all get supplied, but eventually the price of generation keeps inching its way up until they're both 110, and that's the clearing price right there where it crosses. And in this example, both the generation, no, I'm sorry, the load clears at it crosses. Now what you don't see here is it really comes down like this, and the generation comes in with a solid line. I tried it, and it comes across like that. And this is 110. That's the load has the 110 price, not the generator. The generator's prices around there are what we had that before. There's something well below 110, and then there's something that's above it, 120. So that's the clearing right there. As soon as it crosses, this is a picture of what's going on in here. That's it. Now, here we don't. Now the price of generation is above what the load is willing to pay. So there's the rest of this block doesn't get and this final block of load doesn't get sold. Same thing for the generators. Okay, so we can solve this with just the tables like that. Now, what we want to do though is we want to come along and do this with an optimal power flow. And I took a program. I'm going to give you the program, and you can. No, I'm not giving you this program. I'm going to just show you the results here. But this is my standard little my standard DC OPF, okay, and that's a OPF that's based on quadratic programming or linear, and you can put a network into it, and the network can have limits as well as contingency constraints and so forth. And so in this case it's going to do a spot market simulation. You can also, and we're going to get to this next week, you can also put fixed transactions on the market. So we have my 6-bus system, and you can put some transactions onto it. So I said, okay, from 6 to 4, that's a transaction. I think. Let's see. Let me see the diagram here. Where are we? 1 and 6. Yeah, this is. So this is 1, 2, and I should learn to draw it again. Here's 3, and here's 4. This is 6, and here's 5. And so I have a transaction which goes in here and comes out here, meaning I've got a generation source here and a load over here, and it goes through the network. Well, later on we're gonna go through the complexity excuse me. I had to retreat and get a Kleenex, so I've got a little cold. Anyway, the complexity of mixing a dispatch with fixed transactions. If you remember, I said that bilateral transactions can take place on top of this auction. Okay, so let's go through that again. So we have the auction where we're doing minimum CI/PI minus WJ PJ sum PI minus sum PJ equals 0, and then network constraints. And then we can also have transactions. Now, I'm sorry. Here we go. Here, so I can have an auction with the cost for generation minus the benefit function for load, balancing the load and generation, network constraints, and then I can also have transactions, which has a from bus to bus and X megawatts. Now, where do they come from? And what are you doing here with them? Well, the idea is, and we're going to give you, we're going to go through an example next week, and I'm going to give you part of your homework problem is going to deal with this. So you're going to look at it tomorrow. If you get the homework, and you're going to say, we haven't had that yet. No, you haven't, but you will next week. The idea being that I put a fixed transaction on the system. And where did that come from? Well, there's a generating company decides that they don't like to use the spot market for everything. And so they're going to get on the phone and call up the load on the phone, or do it over the internet, whatever, send them faxes, whatever they want to do. And say, I can sell so many megawatts to you for this price, and the load says, that's a good price, I'll buy it. So now it's just a fixed transaction going. There's a fixed input at that bus, and there's a fixed output at the two bus. So we'll generally put this as a generator. It doesn't actually have to be, and this is a load. But it's nice to think of it that way. And they set it up. Now, what we haven't said is how much do they pay for the use of the transmission system. That's another detail that comes up next week. And what it turns out is they have to pay the difference in locational prices. All right, we'll come to where that comes from next week. But initially, in this example that you're going to see in the lecture notes, there's no such transactions. Okay. And so we bid, and this is the result of it. And you will notice that the lambda comes out at the bus lambda comes out at 110. Where did Here it is, right here. Here is the bus lambda on this diagram. It says bus lambda, and so there's 110. This is the clear price, and this shows you all of the bids, and the bids with negative. So positive are generators, negative are the load bids. And you notice bid B and bid C. You can bid. There's no point in bidding a constant. The constant doesn't play in the LP or in the quadratic. So this one will accept quadratic functions, but I just used linear. And here's all the bids from all the generators. So there's and I put them in. I put the generator bids in first. So they're the generator, and they're not in order listed here. It just says, well, this is the bid data that came in, loads, generators, and there's the megawatts, and it tells me the program, the OPF, automatically decides how much load and generation is going to be sold, and that comes out in here. Now, it actually turns out that 200 megawatts doesn't get supplied to buses 4 and 5. That's listed here. Here's the network flows. Here it shows the network flows, and in here it's just saying, well, look, this is the so this is the bidding data, but this is the results in here, and it says at a lambda of 110, these are the bus generation on the different buses, and it adds up the blocks on those buses, and it adds up the blocks of load. Okay, and there are no transactions, so they come out zero. So the OPF actually solves for the optimal dispatch. And the second example now is that we put a limit. We changed the network data so that let me go back here. We said part C. Part D, line 1 to 2 has a 50 megawatt limit. Which is a line. It's just this line right here that's coming here. I'll kind of, we'll just kind of crosshatch it. So in that problem, it's this line right here. Well, what on earth is the result? Let's go back and look at the initial dispatch had the flow on that line at 70. The flow on that line at 70. Yes, I picked 50 to make it to cause problems, and now you end up with contingencies and contingency constraints, and you end up with. So here's a whole list. When it solves with the bids don't change, but the network has now changed. It resolves the whole thing, and you have, if it drops 1 to 4, then line 1 to 2 goes to 50 megawatts and so forth, and it doesn't allow contingencies to overload the system. So we're now solving the problem as a contingency constrained OPF. And suddenly, when we go to this display over here, you notice our friends, the bus lambdas, now are all different. They're all different. Before they were 110, now they're all over the map. Some bus 1 is at 50, all the way up to one of them that's at 200 on bus 4. So we have solved the optimal power flow with this further constraint. Note also that the load that's not served now is higher. By putting a constraint on the transmission system, some additional load is not served, and it's no longer because the generation isn't available, it's because it can't push it through the transmission system. So this shows the power of the LP or the OPF. Really, as I said, here it's using a quadratic program, but it could just as easily be an LP. There's the two constraints down here, and so we have changed the problem. We have changed the problem now. Let's see, I got. No. I've got more output here than I know what to do with, and okay. Oh, then I did the problem again where I said there's no contingency checking. There's a flag that you can set. And I raised the contingency limits. I also turned them off so that you could see the difference. So this is a very powerful tool, but the whole point of today's problem session, the whole point of today's problems, and next week too, is that the auction is done with an OPF. It's done with an OPF. We are trying to hire a new professor at our department. If he decides to come, I will let you know. I don't know. He probably won't be starting until late in the summer. But that's his specialty, is OPF. And I was telling him that there's actually the Federal Energy Regulatory Commission, FERC. This is part of the Department of Energy. That FERC maintains a website specifically with papers on it that describe how to solve the OPF. If the OPF is what's going to run this whole auction, they want to know what the state of the art is for OPF. And so the federal, and they're having a conference. They have conferences about every year or 2 years. I don't know what the cycle is, but to talk about OPF. Okay, so the auction is done with an OPF. Now, just to finish up here, the way it's actually done is, let's say here's Monday, Tuesday. And we've divided the day, so here's 12, 1, 2, 3, etc. And we go over to 10, 11, 12. Okay, and so here's noon, and we so here's 24 hours. And let's say here by 2 p.m. on Monday, people have to put in bids, and they put in. So the generators and the loads enter 24 1-hour bids. They can enter a bid just for a few hours if they want, or they can enter a bid for every hour. They can tell them this bid goes from the whole day, whatever it is. And so you've now got generator bids for every hour of this next day. And then what they do is the OPF is part of a unit commitment. And so when the unit commitment is doing its thing and there's an economic dispatch inside of it, the economic dispatch at each hour for each combination that it's testing out is done on an OPF. Furthermore, it's not just any OPF. It's a security constrained OPF. Okay, so it's doing contingency analysis for every combination of generating units to find the optimum schedule. So we're trying to find the optimum schedule of generators across the next day. And this thing this thing got the abbreviation SCUC, Security Constrained Unit Commitment. Originally done with Lagrange relaxation. So later done with what we call 1-0 programming. CPlex, which was an independent company that got bought by IBM. It's an IBM product now, and that is the modern state-of-the-art way of doing this, because it's doing unit commitment. There's a strong belief. I would say this. It's a pretty good bet that it can get closer to the optimum than Lagrange relaxation. You know, Lagrange relaxation, we had to kind of say, well, how far is that gap? And if the gap is reduced to a small enough amount, okay, we're going to quit. But maybe we're not at the optimum. The desire is to get to, quote, the optimum. And they felt that CPlex is a much better tool for doing that. I'll tell you, there's a new form. I've got one PhD student working on this, but called non-convex programming. If you want a PhD project to look at, there's your challenge. I'll leave that topic. I'm not going to get into that, but this is the way Lagrange, and basically it's running security constrained OPF for each combination of units up, and it does it for 24 hours. So you get a 24-hour unit commitment where the final commitment has been tested against a security constrained OPF. Quite a piece of engineering. My opinion, had not the engineering community developed the security constrained OPF and the unit commitment process around Lagrange relaxation, we wouldn't have gotten off the ground with deregulation. We needed a mechanism to solve this auction. So once again, when you enter the auction, you offer bids for the next day for the hours of the day. Let's get it so you can see it. You offer bids here for these hours, and those bids, you can just bid for a couple hours, but you better have it set up so that you can turn your units on. But they want you to bid them, and you have to get all that in. You send it in electronically to the market 2 p.m. the previous day, and I don't know how long it takes to solve it. So that's the job of the market, and then at a certain point before the day actually starts, they come out with a schedule that says, okay, your generator is going to go on at 2 a.m., yours is going to go on at 5 a.m., and so on, and this is the schedule. Then there's another whole adjustment thing that goes on around that. Okay, we will call it a day here. So once again, we are coming to the end of the course. We only have 4 more problem sessions, and we will see you next week. So the homework 9 will be our final assignment. Will be posted tomorrow, and you will have 2 weeks. You'll have up to the end of the semester to do that. Okay. So we'll bid you goodbye here while I press a button that says leave meeting, end meeting. Bye-bye.